All right, we are diving into chapter 3.2. It's on page 68. We're talking about acceleration still. We got some good views yesterday with our air resistance challenge. You're doing the drops, that you could see how acceleration worked. And I showed you the video at the end of class yesterday, which I think is just a very cool video, showing the feather and the bowling ball. And I'm sure you noticed this, but when they removed the air, could you see that they were exactly falling at the same time? The amount of acceleration they had was exactly the same. Why? Because gravity is the only thing working on them. Gravity is accelerating them. There's no air resistance to prevent gravity from pulling them downward, and so they simply fall at that nice, sustained acceleration. I did want to show you that the same thing, even before that was done, most famously was done on the moon. So let me play this little bit for you here, though I think I might have turned off the sound. I did, so let me do that. Here we go.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
Which is the name of their ship.
Or a falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Drop them here.
Reply here, so watch right here.
At the same time.
Here's them dropping, and they hit the ground at exactly the same time. Now, why does that work on the moon but not here? Because there's no air. Right? You can turn it back on. Thank you. In actuality, they actually even fall slower. The acceleration is slower on the moon because there's less gravity. That's why if you ever watch the video of these guys walking on the moon, they kind of bounce, like they hop, instead of just walking, because it's more efficient. It's easier just to bounce along, like you're in some giant bouncy house, or what's that place called where you have the big trampolines? Sky Zone, that's what I was trying to come up with, yeah. Like one big Sky Zone place. And that's what the moon is like, right? All right. So are you comfortable? And the reason why I wanted to show that to you again, weight does not affect how fast something falls. Weight does not. Because a feather and a bowling ball or a feather and a hammer weigh significantly different, right? But if you take out the air, they fall at exactly the same rate. The reason why in our normal lives we would say, no, the feather falls slower, is because of air resistance. We cool? All right, so let's talk about acceleration. And in particular, we're talking about displacement with acceleration. How far something moves based upon how it's accelerating. So if you remember that we used an equation that acceleration is equal to the change of velocity over the change of time, right? Delta V over T. That is our acceleration equation, right? So acceleration equals velocity over time. And we put that little delta there. The delta just means change in, right? So that means VF minus VI all over T. And physics loves these little subscripts with different things to tell you what it is. So VF just simply means final velocity. VI means initial velocity. And whenever you do change in, you always do final minus initial. Okay? I ignore the delta T because almost always we start time at 0 and then move forward. So whatever your time is usually going to be the time. But if you started at 10 seconds and went to 20, okay, you have to subtract, so you only have 10 seconds you're dealing with. Does that make sense? So in this section, on page 69, they took this equation for acceleration and they rewrote it to give us this equation, that velocity final equals velocity initial plus acceleration times time. If you want to see the math by which they did that, let me show it to you here. Acceleration equals Vf minus Vi all over t. We're trying to get Vf by itself, right? So how do I get rid of the Vi? Vi is doing what to Vf? Well, okay, let's get rid of t first. I'm cool with that. What are we doing with t? Cool. So I multiply over here, right? So those cancel. So now I have Ta equals Vf minus Vi. How do I get rid of the Vi? I add it. This is all easy stuff for you guys. Plus Vi, so plus Vi. So if I rearrange these so I can get it all in the same place, I end up with Vf equals Vi plus At. Does that make sense? All they're doing is just rearranging the equation. Okay? And again, physics loves to do this. We'll give you an equation, and then we'll rearrange it. And then we'll substitute pieces in, because everything's all related, right? So the point of this is telling us, if I want to find out how fast something is going, I need to know how fast was it starting. Did it start at 0, or was it already moving? And then what is the acceleration it undergoes, and how much time is it accelerating? And if I know those things, I can calculate what the velocity is. Okay? So those are the first set of problems. We're going to use this new form of this equation. Again, same equation that we started with, that A equals V over T. We've just rearranged it to solve for Vf. So that's first part. The second part is that we can actually look at a graph or a table. Let's look at the graph here. And we can determine how far something goes, what its position, how its position has changed. In other words, what distance or what displacement it has undergone, just simply by looking at the graph. So here we have a displacement time. So in this case, over time, right, this thing has moved further and further. You see that as time goes on, it's moving larger and larger segments, right? In other words, it's accelerating. If it was going at constant velocity, that would be a nice straight line, right? But because it's this little parabola going upward, it's telling us, hey, it's increasing velocity over time, all right? So we can take a look at a velocity time graph, velocity over time. We cool? And we know that when I take velocity and divide it by time, the slope of that is acceleration. We've already learned that. We've already talked about that piece, right? And the same thing if I go back to this displacement time graph. Displacement over time, the slope of that line is velocity, right? Rise over run is how you calculate slope. So y over x, distance over time, that's what velocity is, right? If I look at the acceleration time graph, the velocity time graph, velocity divided by time, meters per second divided by seconds, that gives us acceleration. I probably better write that down, eh? Would that be helpful for you? So a displacement time graph, the slope is velocity. Does that make sense? Again, rise over run, just so you remember how you calculate rise over run. Or you could say it is y over x. And slope is m. You a math people? Good. Just making sure. It's been a little while since I did that one. If I have a velocity time graph, the slope is going to be what? What does the slope equal? No, because velocity is here. So it would be velocity divided by time. What does that give us? Not displacement. Not distance. Acceleration. Right? Because if I take and I divide meters per second by meters, that gives me meters per second squared. Right? Now to come back to what you said, Nick, about displacement, the area under the graph on a velocity time graph, that is displacement. Or if you want to call it distance, I'm okay with that as well. So what I'm saying is, if I look at this graph, right? If I were to take and look at, oh my, I don't want to move it, I want to write. Will you not let me write? Okay. If I were to take all of this area underneath here, and I were to actually to calculate what that area is, that number would tell me how far this thing traveled over that period of time, going at these changing velocities. Does that make sense? Let's do it with an easier graph first before we try and do it with the triangle. With a linear graph, I mean. Mm-hmm. Times 1/2. You got it. Yeah. No complications at all. Let's use just something that has a constant velocity first, so you can see the piece. Okay? So here, this guy, we want to know what's the displacement after 1 second and after 2 seconds. All right? So how fast is this airplane going? And again, this is in your textbook, by the way. This is on page 70 in your textbook. Example problem number 3. How fast is this airplane going? What's its velocity? 75 meters per second? Okay, you can see that because here's the line, right? Is this airplane accelerating? No. How do you know? The line has a zero slope, right? Yeah, it's not going up, not going down, it is flat. Okay? So it means over the time, and we're only looking at 3 seconds of this motion, the velocity is unchanged. Okay, so if I want to calculate the area underneath, because remember, for a velocity time graph, the area under the curve, or under the graph, that is your displacement, how far you've traveled. Okay? So, if I want to calculate the area here, and we're taking just this 1 second time frame first, right? So we're talking about this area right there to begin with. How would I calculate that? Well, what shape is that? It's a rectangle. How do I find the area of a rectangle? Base times height. Are we cool? It's super easy, right? So, what is the base in this case? What number is the base? It's from 0 to 1 second, so it's going to be 1, right? What is the height? 75. That's the amount of velocity we have there. Notice, of course, this graph doesn't go to 0 on the y-axis, and that's fine. So we'll still use 75. So how do I calculate the area then? 75 times 1. And again, they walk you through this process. I have slides that walk you through the process, but it's kind of like duh, right? I'm just calculating the area of this triangle, of this rectangle. What about at 2 seconds? What if I want to know instead how much displacement have you gone in 2 seconds? Same formula, right? I'm still going to take base times height. So here's my base, but now it's 2 seconds, right? 75 is my height. So 75 times 2. It's 150. 150 what? How far? What units are we using here? 150 meters per second is velocity. Ooh, let's do the units. Let's do the units. I'm getting some good pieces. So we did 75 meters per second, and we multiplied it by 2 seconds. Are we cool? So what happens to these seconds? They cancel, right? So I'm left with my answer of 150 what? Meters. And again, you know this because, maybe I better write this too. These are units I'm assuming you are comfortable with. That distance or displacement is meters, right? That's what we're going to use consistently for our length. And it can be centimeters or millimeters or all the units we learned that are, but meters is your base. What is velocity? What units do we use for velocity? Meters per second. We may also use kilometers per hour if we're talking about like cars, because we'll do a decent number of car type problems. But again, the base units are still meters per second. And then what about acceleration? What are my units for acceleration? Meters per second squared. Because remember, it's velocity divided by time. There's an old saying in physics that if you just look at the units, you can always figure out the equation. If you know how to use the units, you can figure out you don't have to memorize it. It's there. Question?
Why is the United States miles per hour?
Just because we're America. That's why. Yeah, we don't deal with that foreign stuff. I don't know. There's actually laws on the books for us to use the metric system, but we just never spent the money to make the change. Yeah. Yep. It's just because we're America. We do our own thing. Does that make sense, my friends? Okay, let's go back to, because it's easy to do with a rectangle. But what if we go back to that triangle? Stop. What if we instead go back to this lovely triangle? I ask you, if I want to calculate the area here, right? Let's say we're going to go all the way to 4 seconds here. And I want to know this area, right? Anybody have any ideas how I would do that? Nick does, because we just talked about it a second ago. No other ideas? How do you find the area of a triangle? Help us out, Nick. Base times height. Cool. But what else do you have to add to it? Divided by 2, or 1/2 base times height, right? Because that's not a square or a rectangle. It's only half of one, right? So therefore, I would take, in this case, 4 seconds multiplied by, my height is 20, and I multiply it by 1/2. So my answer is going to be 20 what? What units am I finding? Meters. This is displacement. Remember, the area under a velocity time graph is displacement, or distance, how far you've traveled. Oh, I just can't multiply. My apologies. My brain is tired. Thank you. Yes, 4 times 2 would be 8. Divided by 2 would be 4. Well done. Are you with me, friends? Okay? I'm going to pop you ahead just for a moment. Look on page 71. Because on page 71, they show you a combination. This will just help us as you're moving forward here. Boy, sorry, I'm not finding it on my slides here. Here we go. Can you see that this is when I start off with some velocity already? The other graphs were starting at 0 and going upward. This one is already starting with some motion. This is there on page 71. Right? There's already some initial velocity present. So therefore, this is two pieces you have to find the area of. This rectangle on the bottom that doesn't ever go away. Right? And then the triangle on top of that. So we actually have a whole different equation. It's not a different one. It's just spread out more to calculate those pieces. And I'll put it up here just so you can see it. It looks like this. That distance is the initial distance plus velocity times time, and then 1/2 AT squared. We get that because, and by the way, your textbook uses X's instead of D's. This is an older version of this PowerPoint. The point is simply being, we have to calculate this piece, the VI and TF, that's calculating the rectangle part. The 1/2 AT squared is calculating the triangle part. All of that to give us the amount of distance or displacement this thing has. Question, sir? Okay. Okay. And if you want to see how they did that, they show it to you right there on page 71. They explain to you how it was basically because we're substituting V for A, and that's what ends up squaring the T. Okay? We'll talk more about that as we go. Any questions here? The big piece I wanted you to get today was this displacement is the area under a velocity time graph. Okay? As well as this new, in quotes I put new, equation for velocity. That velocity final is initial plus the multiplication of acceleration times time. What I would love for you to spend the rest of this class period, both you guys here in period 3 as well as you folks listening in period 7, is on 3.2. I would like you to do numbers 16 to 18 as well as numbers 20 to 22. That will be due tomorrow for you. Tomorrow, just so you get an idea of where we're going, because again, I will not be here tomorrow and Friday as I attend this funeral. Tomorrow, we're going to look at the Nobel Prize. This is Nobel Prize week, in case you were unaware. They award all the Nobel Prizes on this week. They had medicine back on Monday. Physics was yesterday. This morning is chemistry, if I'm not mistaken. I haven't even looked at the news yet, so I don't know what won. Anyway, I have some articles I want you to read about the Nobel Prize for Physics. It was on lasers this year. And actually a woman was one of the 3 Nobelists, which there's only been 3 women in like the whole time they've been giving the physics award, which is a big deal. It's a very big deal. So I want you to do some reading and do some reacting to that. On Friday, there's a study guide. And then when I say study guide, not my kind of study guides I write out for you, but a study guide the book does that has some problems and questions on Chapter 3 that I want you to work through. Some of the Chapter 3.3 stuff you won't be able to do yet. I'm fine with that. We'll talk about that more when I come back. Okay? But the key is I want you to get comfortable using the equations in Chapter 3 to determine acceleration. Are you with me? Yes. Those of you on the video, you're with me? Good. All right.